Hey everyone, welcome back to Calculus 3. This will be lecture 14 of the course. And in this section, we're going to get into a very interesting area of calculus, and that is partial derivatives. So let's go ahead and jump into it. So this will be section 3.3 of this course, and we're going to call it partial derivatives. So we've been talking about functions of several variables, and it's natural to ask the question, how will a function be affected by a change in one or more of its independent variables? Okay, so how will a function be affected by a change? We'll start with this, in one of its independent variables. Okay, so if I've got a function of x and y, what happens if I just tweak x a little bit or change x and leave y constant? What happens? Well, this is the domain of partial derivatives. All right, so to answer this question, we need to define what we mean by a partial derivative. Okay, so let's go ahead and define the partial derivative. Okay, so if z is a function of x and y, then the first partial derivative, okay, of f with respect to x and y with respect to x and y are the functions. We denote it like this: f with an x subscript and f with a y subscript. So this is the partial derivative of f with respect to x. This is the partial derivative of f with respect to y. Okay, and so they're defined by, and this definition will be very straightforward if you've been following us up through Calculus 1. So f of x, f sub x of xy, so the partial derivative with respect to x, this is equal to the limit as delta x goes to 0 of f of x plus delta x comma y minus f of x comma y over delta x. Okay, and just for completeness sake, let's put in the partial derivative with respect to y. That's going to be x comma y. It's equal to the limit as delta y goes to 0 of f of x comma y plus delta y minus f of x comma y all over delta y. Okay, so what's happening here? What's happening in this definition? Well, when we differentiate with respect to x here, you'll notice that we're allowing just for the variation in the x variable. With y is treated like a constant variable, right? So you have the limit as delta x goes to 0, so you're just off of x, and there's a small delta x here, right? And it's basically the same definition as we saw in Calculus 1 of the derivative of f of x with respect to x, except here you've got the y variable included as well, acting as treated as though it's a constant in the function. And similarly for the partial derivative with respect to y, you allow y to vary, y plus delta y here, and you take the limit as delta y goes to 0. Right? So this is almost the same idea as what we had in Calculus 1, but here you just have this extra variable which, for all intents and purposes, gets treated like a constant. Okay, and we should say that these are the partial derivatives provided the limit exists. Right, it may not. Right, meaning the function may not be differentiable. Okay. Okay, so so you can see basically the same idea as what we had with regular, or what we call ordinary derivatives. But here you have this x. If you have multiple variables in the expression, you differentiate with respect to only one of them. The other variable gets treated as though it's constant. Okay, so let's see an example of how we can do something like this. Okay, so let's find the partial derivatives f of x, f sub x, and f sub y for the function. And let's say we've got f of x comma y equals 3x minus x squared y squared plus 2x cubed y. Okay, so nice polynomial here. And we're asked to just find the two partial derivatives. Partial derivative with respect to x, partial derivative with respect to y. And so we'll start by trying to find the partial derivative with respect to x. So here's the way to think about it. You want to consider y to be constant. So considering y to be constant and differentiating with respect to x, okay, produces what? Well, so the first term here, 3x, so that's 3 times x. We're differentiating with respect to x, so that just becomes a 3, right? So this would be 3. And then what happens here? Well, remember y squared is a constant when we're differentiating with respect to x, so this would be 2x y squared. Oh, actually minus 2x y squared. Okay, and then what about over here? Well, again, y is constant, 2 is constant, so this would be 3 times 2, so 6x squared y. Okay, so that's the idea. So you kind of go through this, and everywhere you see a variable that isn't the variable you're differentiating with respect to, you treat it as a constant. Right, and then obviously you treat the constants as a constant. Okay, let's try the other partial derivative. The other one we're looking for here is f of, well, let's rewrite the function so we can look at it. So it's 3x minus x squared y squared plus 2x cubed y. And now we want to find f of y, f sub y. Okay, and so here we would say, okay, what about this first term? Well, the first term, when we're differentiating with respect to y, is basically constant, right? So that just becomes a 0. What about over here? Well, the x squared is treated as a constant, and we're differentiating with respect to y. And so this would be 2x squared y. Okay, and then over here, the 2x cubed, think of that as a constant, and so differentiating with respect to y, we're left with just the constant, so 2x cubed. Okay, so the partial derivative here is negative 2x squared y plus 2x cubed. Okay. Okay, and so that's the idea with partial derivatives. I mean, it's somewhat straightforward actually, but of course, you know, complexities can arise, and these kinds of functions you're dealing with can be as complicated as you can imagine. Right? So let's talk through some of the notation that's used for partial derivatives. Okay, so some of the notation. So for z equals f of x, y, the partial derivatives f of x and f sub y are denoted by, now there's lots of different ways to denote these things. Here's some of the more common ones, right? So you've got your f of x, f sub x of xy. Another way to do it is to do notation similar to the ddx, except the script is different. So this is more like del x. Okay, it's kind of a lowercase cursive d. Okay, and it's actually flipped backwards as well. Right, so it looks like this. Right, and this just indicates a partial derivative with respect to x. Okay, another way to write it would be to say z sub x, right? So z is equal to f of xy. And then yet another way would be using the del notation again. You'd get del of z over del x like that. Okay. And of course with y, you would have the same thing. F of y, f sub y of xy, del y of f xy, z sub y, or del z del y. Something like that. Okay. All right. And let's see. So these are common. I mean, I think actually all of these are pretty common. They're commonly used. I mean, these are all highly relevant notations. And sometimes you'll be asked to evaluate partial derivatives at a particular point, and frequently those evaluations will be notated in a particular way as well. So if evaluating a partial derivative at a particular point, sometimes the notation will look like this. Right? Or, I've seen it like this. Something like that. Or, let's see, you could also do this kind of thing, of course. Evaluate the actual function there, like that. Okay, so these are just the cases where you got to plug a value into a partial derivative. And so how would we notate that? This is common. Okay, let's do some examples. See if we can get comfortable with these. It's a lot like regular differentiation. You just have to be able to sort of shift how you think about the other variables in the expression. You have to be able to shift those other variables into, the mindset of, hey, these are constants now. So, okay, here's an example. So for f of xy equal to x times e to the x squared y, okay, so you got this function of x and y. Let's find f sub x and f sub y and evaluate each at the point 1, ln2. Okay. Right, so this is a function of x and y. Let's evaluate each of these at the point 1, ln2. So let's go ahead and try to differentiate. We'll start with the partial derivative with respect to x. So f of x, y, and I'm just going to be very intentional with all the notation here, just because we're learning. So that's del x of x e to the x squared y. Okay. And now this is going to be the product rule, right? You've got a function of x over here, and you've got e to the x squared y over here, two functions multiplied together, so we can use the product rule. And so we'll do this, del x of x times e to the x squared y plus x del x of ex squared y, right? So this is just an old familiar product rule, right? Works the same way. Okay, we differentiate x with respect to x. We're left with just a 1, and then this stays as before. And then we've got the x here, and then the derivative here is, what are we going to have to do here? Well, for this part, we're going to have to use the the chain rule, right? So you've got the outside function is e to the u, and then u is x squared y. Right? So this would be e to the x squared y power times the derivative of x squared y with respect to the partial derivative of x squared y with respect to x. Let me actually write that in just so that that's clear. So it would look like that. Right, so you've still got the 1 here, e to the x squared y, plus x e to the x squared y, and then this last piece here is 2xy, right? Okay. And so kind of cleaning everything up, the derivative here would be e raised to the x squared y power plus, now what's going on here? We've got 2x squared y times e to the x squared y. Okay. And so this would be the partial derivative of f with respect to x. Now, can we evaluate this at the point 1 natural log of 2? Sure. So f sub x evaluated at 1 comma ln 2. Well, you're just going to plug in a 1 everywhere you've got a x and an ln2 everywhere that you have a y. So this would be e to the 1 squared times ln2 plus 2 times 1 squared ln2 times e to the 1 squared ln2. Okay, and so this would be e to the ln2 plus 2 ln2 e to the ln2. And then, of course, all of these e to the ln2s are just 2, so this is 2 plus 2 ln2 times 2. And so you get 2 plus 4 ln2. And so that would be kind of the final answer for that. Okay, and so we could do the same thing for the partial derivative of f with respect to y. Okay, so let's take a look at the other one. Okay, so for f of y, it's going to work the same way, except you have to be a little bit cautious here, right? So let's set this up like, so this would be del y of x e to the x squared y. Okay. Now, in the previous example, we used the product rule, right? Because we had x times e to the x squared y, right? So it's kind of a product of two functions. Now, that was with respect to when we were differentiating with respect to x. Now, when we differentiate with respect to y, things are different, right? Because in the case of the partial derivative with respect to y, x is just a constant. So you could think of this as 2 times e to the x squared y, or 10 times e to the x squared y. You don't have to use the product rule if this is the number 10, right? Well, it's the same situation here with this partial derivative with respect to y. This x is treated like a constant, right? So let's write this down. No product rule is necessary because x is treated like a constant. Okay, so this one is quite a bit easier to sort out. Right? So in this case, we would you could just factor the x out. You think of it as like a constant. So this could be like x times del y of e to the x squared y. Right? And so that would be x times, and then you still have to use the chain rule here. Right? So but that's going to be x times e to the x squared y, and then you differentiate the x squared y piece. So x times e to the x squared y times, now what's this derivative with respect to y? It's just going to be x squared. Okay, and so this whole thing is just x cubed times e to the x squared y power. Okay, so somewhat simpler derivative to calculate. Okay, how about evaluating this derivative at the point 1 comma ln2? Well, let's do that. F sub y at 1 comma ln2. Well, again, you're going to plug in a 1 where you got x's and an ln2 where you have y's. And so this is 1 cubed, right? That's this one. And then it's e to the 1 squared times ln2. All right, so this is just e to the ln2, and so this one is just equal to 2. Okay, so different answers, right? So f of x, f sub x, the partial derivative with respect to x, at 1 ln2 was equal to 2 plus 4 ln2, and the partial derivative with respect to y at the same point is equal to just 2. So you get different answers there. Right? And so this is going to kind of push us in the direction of the next example. What are these? How should we think about these different values here? So these are numbers, right? So what does this 2 represent? Well, this is telling me the slope of f in the direction of the y-axis at this point 1 comma ln2, right? So there's a particular slope of 2 there. Now for x, at the same point in the direction of x, the direction of the x-axis, the slope is different. It's 2 plus 4 ln2. Right? So you have different slopes for these different directions. Okay, and so that's going to lead us directly into the next example, which is going to explicitly ask us to find these slopes. Okay, so let me actually flip pages here so we can get it all on one page. Okay, so example. Let's find the slopes of the surface given by, now here's the function, f of xy equals negative x squared over 2 minus y squared plus 25 over 8. Okay, so find the slopes of the surface given by this function at the point. Okay, at the point. Now the point is going to be 1/2 comma 1 comma 2. And we want to know the slope in the x direction and in the y direction. Okay. All right, so let's first answer the question, and then I'll draw a picture. I'll attempt to draw a picture. Well, you know what? Let me try to draw the picture first. It might be useful to see. The problem with drawing the picture is that it's a difficult picture to draw, and I don't want it to be more confusing. But let's just try. Let's just see what happens. Okay, so this function f here is going to produce a curve in 3-dimensional space, and it kind of looks like this. Okay, this is a big kind of here. Okay, and so this has got some kind of a right. So there's like this kind of thing on the front here, and it just, whatever it does beyond this is irrelevant. But so what we're interested in, there's a particular point here, and it's going to be 1/2 in the x direction. So we'll say this is the x, y, z axis. So it's 1/2 in the x direction, 1 in the y direction, and 2 up on the z axis. So let's just put it on here. We'll say it's right about there. There's going to be this point on this surface. And what we want to know is what is the slope of this guy in the x direction, right? So coming up this surface, there's some kind of a slope, right? If we travel parallel to the x-axis on this curve and we cross through this point, what's the slope at that point? And similarly, if we're traveling parallel to the y-axis on this curve, on this surface, and we pass through this point, what's the slope? Right? So you've got kind of these two things. You've got something going like this and something going like this, and we want to know the slopes. Okay, it's very hard to represent three-dimensional surfaces like this in drawings, but hopefully you get the idea, right? You've got this surface in space, you've got an x direction, a y direction, you've got a point on the surface. What is the slope at that point? That's what's being asked here. Okay, so to find the slope in the x direction, we just need the partial derivative with respect to x, and so we need to calculate this. Okay, and so that's pretty easy to do. This is going to be, you can think of, well, this is going to be negative 1/2 times x squared, and so when you differentiate with respect to x, you get negative 2x squared over 2. This is treated as a constant, so it just disappears. Same as this. This is also a constant, right? And so what we end up with for the partial derivative with respect to x is just negative x squared. Okay. And can we figure out what the slope is here? Yep. F of x, and now x and y here, you're going to plug in 1/2 and 1, right? So this would be f sub x of 1/2 comma 1. Well, there's no y in the expression, so this will just be negative 1/2. Okay. Oh, that should be not squared. Sorry. Right. So the slope, so this is the slope in the x direction. Right, and that maybe makes sense, I guess, if you can imagine what this looks like. We're obviously heading, we're obviously heading up the hill here, and this is the negative x-axis this direction, so that'd be positive x over here. Right, and so this looks right to me. Okay. Then what about the slope in the y direction? Well, in the y direction, you've got to calculate this guy. Okay, and so similarly, this is a constant term, this is a constant term, and so you just get negative 2y. And can we evaluate the function at 1/2 1? Yes. So this would be the partial derivative with respect to y evaluated at the point 1/2 1. That's going to be equal to negative 2 times 1, so negative 2. Okay, and so here, this is the positive y-axis. We'd have to come down the slope here, and so that's why you would see a negative slope there. All right, very good. Right, so we would say, what would we say? We'd say, so negative 2 is the slope in the y direction. Okay, very good. All right, let's try another one like this. Let's see if we can do another one, maybe one that's slightly easier to draw. That one was very, very difficult to draw. Here's another example. Find the slopes of the surface given by okay, now our function is f of xy equals 1 minus, and then it's going to be x minus 1 squared minus y minus 2 squared. Okay, so find the slopes of the surface given by this function at the point 1, 2, 1. Okay, and we want to specifically find the slopes in the x direction and in the y direction. Okay. All right, so again, simple simple derivatives to find, right? So let's first find the partial derivative with respect to x, right? And that's just going to be del x of this. And so again, I'm just using different notation here to kind of get people comfortable, see where how all this notation kind of fits together. Okay, and so in this case, this term out here is a constant, and so is the term up front. The only one that matters is this guy right in the middle. And so that's going to be a simple chain rule kind of thing, right? So this would be 2 times, actually negative 2 times x minus 1, right? And then the derivative of the inside is just 1, so I'll leave that off. And for the partial derivative with respect to y, similar. Okay, so again here, these front two are now constants, and the only one that matters is the rear. So that's going to be negative 2 y minus 2. And again, derivative of the inside would just be 1. Right, so we just leave it off. What about the slopes? Well, then f sub x of evaluating at 1 and 2. Right, that's going to be negative 2 times 1 minus 1, so 0. Okay, what about the y derivative? That'll be negative 2 times 2 minus 2, so again 0. So in this case, both partial derivatives are in agreement at this point. Okay, let's try to draw a picture here. Again, these pictures are very tricky, so I will do my best here. But so let's say you've got, well, I'm just going to draw the shape and show you what the point looks like. So the actual shape here is kind of like this, kind of dome-shaped, right? And then it kind of looks like that. And then behind it here, right? So this has got some. This is a three-dimensional, kind of like almost kind of like a cone, but a little more rounded. Now, right at the very top is the point 1, 2, 1. Okay, and so maybe your x-axis is in this direction, and your y-axis would be perpendicular to that, or something like that maybe. Okay, and so the slope in the x direction is perfectly flat, and the slope in the y direction is perfectly flat as well, meaning it's parallel to the axes. Right, so this one here is meant to indicate that it's parallel to the x-axis, and this one here is meant to indicate that it's parallel to the y-axis. And so that's how you have a slope of 0 for both of them, right? Because they're both, at this point, the slopes are, I mean, this is kind of like the top point, the topmost point of this shape. Okay. Okay. Very good. All right, hopefully that was helpful. Now, partial derivatives can be used in other types of examples. Really, like, no matter how many variables are involved, partial derivatives can be interpreted as rates of change, right? And so that's what this next example is going to be. So this one is going to involve a parallelogram. So let's write out what we're after here. The area of a parallelogram with adjacent sides little a and little b, and included angle theta, is given by, okay, So this will be the area. So big A equals AB sine of theta. Okay, now let's draw this out really quickly here. Okay, so maybe this is your B, and you've got this kind of shape coming up here, and then how far out? So we'll go like so. And so you got a parallelogram. This will be your A up top here. Oh, sorry, that's not A. Sorry, this is A. Adjacent sides, A and B. So if this is B, adjacent side would be this other guy. Okay, and the area here is AB sine of theta. And so here's your theta. And so kind of the way you would think about this is that the height here is going to be A times sine of theta. Right, so that's recall how to calculate the area of a parallelogram. It's going to be basically base times height. And so B is the base, A sine theta is the height. That's where you get the areas AB sine theta. Okay. And so this is the kind of the setup, and then two questions. Find the rate of change of A of A with respect to little a for specific values. A equals 10, B equals 20, and theta equals pi over 6. Okay, so what's the rate of change of the area with respect to this side? Right, so if this side is a little bit smaller, how much does it impact the overall area? And specifically at these values, A equals 10, B equals 20, theta equals pi over 6. Okay, that's the first one, and then we'll do one very similar. Let's find the rate of change of A with respect to theta for the same values. A equals 10, B equals 20, theta equals pi over 6. Right, so in the first one, the question is how much does the area change when we change A, little a here? Right, it's ever so slightly. What's the rate of change? And the second one is similar, except in this case we're changing the angle. So how much does the area move as theta changes? Right, but A and B are held constant. Okay, so that's the idea. And now can we do this? Well, I mean, just thinking this through, this is item 1 is just a partial derivative with respect to A, evaluated at these points. Item 2 is just a partial derivative with respect to theta, evaluated at these points. Very different derivatives, right? Here's your function. Very different derivatives, but the blueprint is straightforward. Okay, so let's see here. So to find the rate of change of A, big A, of the area with respect to little a, what are we going to do? Well, we will hold B and theta constant and differentiate with respect to little a. Okay, all right, so what does that amount to? Well, that's going to be del A over del little a. Right, so we have to find that derivative. So del A of AB sine theta. Well, in this case, when we're differentiating with respect to little a, this is the variable and this is all just a constant. So this is like 3x or something. Can we differentiate that? Very much. Yeah, easily, right? So this would just be b times the sine of theta. Okay. Right, so b sine theta. And then we have to evaluate this at, a equals 10, b equals 20, theta equals pi over 6. And so that would just be 20, right, so we're evaluating this, 20 times sine of pi over 6, which is 20 times pi over 6. That's sine of pi over 6 is 1/2. And so this is 10. So the rate of change of the area with respect to the side A is 10. All right. What about for 2? Well, very similar, right? So with 2, to find the rate of change of the area with respect to theta, we're going to hold A and B constant and differentiate with respect to theta, right? So instead, we'll do this, del A, del theta. Okay, and so we need del theta of AB sine theta. Right, so in this case, A and B are just constants, but we need to differentiate sine theta with respect to theta. So the derivative of sine is cosine, right? So this would be A times B times cos theta. Okay, and then evaluating this at A equals 10, B equals 20, theta equals pi over 6, we would get 10 times 20 times cosine of pi over 6. Okay, and so this would obviously be 200 times whatever cos of pi over 6 is. And if you recall, cos of pi over 6 is the square root of 3 over 2. And so this is going to be 100 times the square root of 3. Okay. Right, so no matter how many variables are involved, partial derivatives can be interpreted as rates of change. And so in this case, we see that the rate of change with respect to theta is much larger than the rate of change with respect to the side A. Okay, and hopefully that makes sense, right? If theta's flattening out, then the area is changing really dramatically, whereas if A just changes a little bit, you're just adding a little bit more to the height. Well, you're adding a little bit extra up on top here. Okay, so I think that makes sense and is intuitive. Excellent. All right. Let's see some more examples of some of these derivatives with more variables. Okay, so let's try a simple one. Well, yeah, not too hard, but let's find del f del z for f of x, y, z. So you got 3 independent variables here, and this will be xy plus yz squared plus xz. Okay, so same idea as before here. It's just that in this case you have to hold in your mind x and y as constants, and z is the only variable. Right, so this whole term here, for example, is a constant, and so it goes to 0 when we differentiate with respect to z. These two will stick around. So del f del z is equal to, again, kind of using the notation, getting comfortable with the notation here, xy plus yz squared plus xz. And so this guy here, again, this is a constant, so that's going to be 0. And then this is going to be 2y times z. And this will just be x. Okay, so this would be 2yz plus x. Okay. What about this one? What about this example? Let's find del f del z for f of x, y, z equal to z times the sine of x, y squared plus z x, or plus 2z, sorry. Okay. Let's try this one. All right, so this would be, let's see, del f del z is del z of this. Okay, now what are we going to do here? What's going to have to happen? So we've got a z here, and we've got z's over here. So this is the product rule, right? You can think of this as the product rule. And so we can differentiate, so we can do something like this. This will be z times the partial derivative with respect to z of the sine part, plus partial derivative with respect to z of the z times, and then the sine part, unchanged. Like so. Okay. And so this is, obviously the z stays there, and then what happens here? Well, this is a chain rule, right? You'll have to do cosine on the outside and then times the derivative of the inside. So this would be cosine of xy squared plus 2z, then times the derivative of the inside. And so we're differentiating with respect to z, so this can be thought of as a constant, and then it's just plus 2z, so the derivative is just 2 of the inside there. And then this is going to be 1, and then naturally times sine of xy squared plus 2z. And so altogether, you would have what? You would have 2z times the cosine of xy squared plus 2z, and then plus over here just the sine of xy squared plus 2z. Okay, so this would be the derivative. All right. Okay, very good. So that's kind of an introduction to partial differential equation, or sorry, partial derivatives. And just like with other just ordinary derivatives, we have the ability to take higher order derivatives. Okay, so higher order partial derivatives, right? So similar idea to what we had with ordinary derivatives. Just the notation is a little bit different, and there's also a few additional cases to consider. Okay, so we can take second derivatives, third derivatives, higher order derivatives. So let's just talk about second derivatives first, and the third higher orders I all kind of follow on here, but there are a couple of different options for the second derivatives. Right? The first one is kind of like the normal second partial derivative with respect to x example. So if, say I have the partial derivative of f with respect to x, and I differentiate that with respect to x, partial derivative with respect to x of that, then that's going to give you what's called the second derivative. Okay? And it's notated like this frequently. Another way to write it, pretty common, is to have f with double x subscripts, like that. Right? This is the second derivative. With respect to x. Okay, basically just do it twice, just like with a regular derivative. Okay, and then of course, naturally, you can do the same thing with y. Right, and it's denoted similarly. And so this is the second derivative with respect to y, naturally. Now, what's kind of different here is that you can get what's called a mixed partial derivative, right? And so what does this amount to? Well, if you start with, let's say, the partial derivative of f with respect to y. You start with that. And let's say we then differentiate this. We then take the partial derivative of this with respect to x. Right? So if I do one of these to it. Right? So I've got the partial derivative with respect to y, and I get some function. I then differentiate that function with respect to x. Right? So it's like taking a higher order derivative, except on the second differentiation, you differentiate with respect to a different variable. Right? Well, this is notated like, similar to what we have up here, except instead of del y squared or del x squared, you get a del x, del y in the denominator, right? And similarly, here you would have f of y, f sub yx, right? So the first derivative was y, the second derivative that you took was with respect to x. Okay, and now this is what's called a mixed partial derivative. Okay, this is what's called a mixed partial derivative. Okay, and similarly, you could do the same thing with, you could take the derivative of f with respect to x first, and then differentiate with respect to y, right? And you would get f of x, y. Okay. Now, these are arrived at 100% based on the order, right? If you start with y and then x, you get this guy. If you start with x and then y, you get that guy. Okay. Let's take a look at some examples. Let's start with an example here. So let's start with this one. Find all of the second derivatives of f of xy equals 3xy squared minus 2y plus 5x squared y squared. Okay, so you've got this derivative, or sorry, this function, and we want to find all the second derivatives of this guy. Okay. Well, so we'll start with just the first derivatives. Naturally. Right, so f of f sub x, right, that's del x of this guy. Okay, and for that we would get 3y squared plus 10xy squared. Okay, so this guy in the middle in particular is just a constant. Now what about the derivative, partial derivative with respect to y? Same thing here. Of course, the derivative is different. You get 6xy minus 2. That one, in this case, this is not a constant. Plus 10x squared y. Okay, so there's the first derivatives. These are the first derivatives. Okay, now we can, using these, we can just identify the second derivatives, right? So the second derivative with respect to x is just the derivative of this with respect to x. The second derivative with respect to y is going to be just this one differentiated again with respect to y. And then the mixed derivatives is where we differentiate this with respect to y and then differentiate this with respect to x. All right, so we'll go through this. Okay, so we'll go through this one. So fxx is where we'll start. This is going to be del x of del f del x. And so that's del x of whatever we got for this guy in the previous example, and what we saw was that's 3y squared plus 10xy squared. And we could differentiate that with respect to x. And again, this is a constant, and this one is 10y squared times x. And so this would just be 10y squared. Okay. What about fyy? Well, that's going to be this partial derivative with respect to y of the partial derivative of f with respect to y, the one we just found. Okay, and so that is going to be 6xy minus 2 plus 10x squared y. All right, so when we differentiate this with respect to y, this is a constant, but these outer two are going to stick around. So you're going to get 6x plus 10x squared. Okay, so those are kind of the straightforward ones where you're differentiating again with respect to the same variable. Now, what about the mixed derivatives here? So in particular, let's look at f of x, y first. So this is going to be del y of del f del x. Okay. And so here we had 3y squared plus 10xy squared, right? So same function here, del f del x, del f del x. Now here we're going to do something different than what we did up here. Here we differentiated with respect to x, and here we're differentiating with respect to y. Okay, when we do that, we get 6y for this piece, and then 20xy. Okay, so that's the mixed derivative xy. Okay, what about the other one? F of yx. Well, this one's similar, but here we're going to do del x of del f del y. So that's del x of, and now in this case, we're taking the derivative of this one. Sorry, this one. No, sorry, not that one. Yeah, this one. The first derivative with respect to y. So that would be 6xy minus 2 plus 10x squared y. Okay, and we differentiate this with respect to x. So here we're going to get a 6y. This middle term is a constant, so it drops out to 0. And then we're going to get over here, we'll drop the power on x down by 1 and multiply the coefficient by 2. So this will be 20xy. Okay. Excellent. So you notice here, I'm sure, that f of xy equals f of yx. That's not a coincidence. The mixed derivatives will generally be equal to one another. Okay, that's going to be the case in general. Okay, and so we'll kind of end this session with this last theorem here. Okay, and what we'll say here is that if f is a function of x and y, if f is a function of x and y such that f of xy and f of yx, f sub xy, f sub yx, the mixed partial derivatives here, are continuous on an open disk R, then happily, for every xy in R in the open disk, the mixed partial derivatives match. Okay, so the mixed partial derivatives match, which is what we just saw in the previous example. So it was not a coincidence. It wasn't we didn't gin up this nice polynomial that happened to have this property. This is true in general. Okay, now the functions have to be, first of all, the second derivatives have to exist, and they have to be continuous on the open disk R. Now, if all bets are off if there's lack of continuity, right, or some other issues that happen inside this open disk. But if the functions are normal and continuous here, when I say normal, you know what I mean, continuous, then yeah, in general, the mixed derivatives will be equal to one another. Okay. All right. So I think we'll end the video or the section here, and next time we'll get into what are called differentials, and we'll continue to explore the idea of partial derivatives probably for the rest of the course. Okay, so this is kind of just an intro, just a little bit of the mechanics of them, but we'll start using them and digging into some very interesting applications of partial derivatives in the coming lectures. So take care. See you all then.